In a previous video, we looked at periodic structures, and we've seen that if you have, for example, a layered stack of different materials, like so, alternating between high index and low index materials, and if you extend this semi-infinitely, for example, in this direction, and if you then have a plane wave which hits this periodic structure like this, then we've shown that there's basically a band gap that opens up, meaning that all the light gets reflected at that interface because there's no propagating states that exist in this semi-infinite periodic structure. So last time we said this opening of a gap follows from numerical simulations, but the question is now, can we give a little bit more insight in why this thing actually opens up? And there's two possible explanations we can give for this. One is a more straightforward one based on interference from different reflections, and another one is a more interesting one. But let's start with the most straightforward one. Pause the video and see if you can think of a possible explanation why under certain circumstances we would have a band gap that would open up. So pause the video and think about a possible justification for the fact that this thing acts as a perfect mirror. So if this wave hits this first interface, part of the light will get reflected and part of the light will get transmitted to the next interface. And then this procedure will repeat. So then basically at each of these interfaces, we will get a partial reflection and also a partial transmission. And basically all of these things will interfere in a very complex way. So obviously you can calculate what the effect would be when you add all of these individual contributions together. But here, for our purposes, it's enough to sort of like understand that it's possible that you can have a certain situation where all of these reflections from all of these interfaces here, they will add up constructively, such that you get one giant reflection in this direction, while at the same time, all the contributions from all the transmissions at the individual interfaces, they will interfere destructively, such that there's no light that's going to be transmitted here. So one possible explanation for our band gap is that it's just a consequence of lots of reflections that are all adding up and then coherent and then constructive and destructive interference. So that's the straightforward approach, but let's now also try something which is a little bit more convoluted, let's say, a little bit more hand-wavy, but still quite fun and educational. So let's see if we have a different way of explaining the origin of the band gap here. And let's again turn our attention to the band diagram. So we have here K on the horizontal axis and omega on the vertical axis. And we've seen in the previous video that our bands here will look something like this. And let's focus our attention here on the edges of the Brillouin zone, which is where the band gap opens up. And numerical simulations show us that the slope here of these bands, they're all horizontal. So we basically end up with what's called flat bands. Now, the question is, physically, what does this zero slope here, what does this horizontal tangent mean in terms of wave propagation? So pause the video and see if you can figure out what the physical meaning is behind these flat bands at the edges of the Brillouin zone. So if you just look at mathematically what's happening in this omega versus k diagram, we have a horizontal tangent. So this means that the derivative of omega with respect to k is equal to 0. Now you might remember this, the omega dk, because that's of course the definition of the group velocity. So the physical meaning behind these horizontal bands is that we have a mode with 0 group velocity. Now, if you have 0 group velocity for your mode, that basically means that the mode does not propagate, so rather we have a standing wave here. So that's a very important realization. At the edges of the Brillouin zone, we're dealing with standing waves. Okay, let's take this one step further and let's ask ourselves the question, what is actually then the wavelength, the spatial wavelength corresponding to this standing wave at the edge of the Brillouin zone? So pause the video and see if you can calculate the value of that wavelength. So we know the values here at the edge of the Brillouin zone. So this is 0, this is pi over a, and this is minus pi over a. So if we're looking, for example, at a situation where k is equal to pi over a, we also know from the definition of k that this is equal to 2 pi over lambda. So from that simple equation, we can derive that lambda is equal to 2a. Okay, that's interesting. So now what we're going to do is we're going to look at the situation where the refractive index contrast is actually very small, infinitesimally small. And the reason we're doing that is because then we can say with confidence that the shape of the modes, for example, will more or less look still like the shape of the modes in free space. So if we're looking in free space and we're looking at a standing wave in free space that will be formed by two counterpropagating plane waves, and they will add up to have like a sinusoidal pattern. And then we can say, okay, if you have a very small index contrast, the shape of that mode will still be roughly sinusoidal. So what we're having is a sort of like sinusoidal wave that looks like this. And we just calculated here that the wavelength here is 2 times the lattice constant. And this is a standing wave. So the thing does not move as a function of time. So bringing all of this together, this means that we sort of like have to find a way to position a standing wave. Again, it's standing, it's moving, so we need to find a fixed position of the standing wave. A standing wave with period 2a. We need to position this inside of our periodic structure. Our periodic structure has period a, like so. So this is here period a. And what we need to find the way is sort of like a way to position this top pattern in this bottom pattern in such a way that it also still respects all of the symmetries that are present in this system, because this system has lots of symmetries. For example, it has inversion slash mirror symmetry here at all of the midpoints of our layers here, because that's how we constructed it. Okay. So now your goal is to pause the video and think about the different ways you could position this particular wave with wavelength 2a inside this structure such that it still respects all of the possible symmetries that are present in this system. Good luck. Right, let's redraw this a little bit to make it a little bit easier. So we have, for example, our first layer over here, and then we have the second one. Okay. All right. So I think that's quite enough. Let's draw some zero line to make it easier for us to position the modes. And so basically what we need to do is we need to find a way to also respect the symmetries of the system. So this means that at the midpoints over here of both the high index and the low index layer, the mode should be either even or odd because we have inversion symmetry with respect to the z coordinate. So one way we can position this mode is by doing the following. And let me just draw a couple of points to make it easier for myself to draw the modes. So if we now draw our sinusoidal profile, something like this, we see that we've achieved what we set out to do, right? Because first of all, the wavelength of our mode here is indeed 2a. It covers 2 periods of our periodic structure. And if you look at the midpoints of all of the different layers here, you see that either we have an even mode or we have an odd mode. This is one possible way of positioning this pattern here such that it still respects all of the symmetries. However, there's a different way of achieving the same thing, and that's just by moving the position of where the maximum occurs. So if we now have something like this on the other hand, so if I now draw my sinusoidal function like this, we still end up with something that satisfies the same boundary conditions, right? The only thing that happens is that whereas in one position it was even, now it becomes odd. but it's still a valid solution of a standing wave. Remember, it's very important that this is a standing wave, because then again, the maxima and the minima don't change in position. So we have a situation that obeys everything that we set out to achieve. Now, let's look at what we have for these two solutions here. So if we have here that N1, for example, is the higher index material, then you see that in the top case, we have concentrated most of the light in regions where there's low index material, because in the high index material N here we have zeros, and here in the low index material we have maxima. Whereas in the bottom situation, it's the other way around. There we manage to concentrate most of the light in regions with high refractive index, because the maxima are occurring at positions where we have N1. You might remember from a previous video that we've derived some sort of heuristic that will tell us something about the relationship between how much of the light is concentrated into high index regions and its corresponding resonance frequency. So see if you can recall what that was all about, and see if you can derive then what the consequence of this would be for our particular situation. So a heuristic we've derived in a previous video is that light likes to be in regions with a high refractive index. That's then energetically favorable, and then that will result in a lower frequency. So if we have the case over here with this bottom profile, there we see that light has its maximum in the high refractive index region. So therefore we can say that the frequency of this particular mode will be lowered, right? Whereas on the other hand, in this region over here, it's the other way around. So light will be more concentrated into the lower index materials. So therefore, its resonance frequency will actually increase. So that explains why there's a frequency difference, a resonance frequency difference between these two modes. And if there's a resonance frequency difference, that means that there's a gap opening up. Because again, let's start from our situation where we had zero index contrast. If we just look at the edge of the Brillouin zone, these two modes, they are equivalent in position and they have the same resonance frequency. But as soon as we have some sort of index contrast happening, then we have slight changes that are happening, such that if you look at the resonance frequency between these two modes, that they will be different. So indeed, this heuristic explains, because of the difference in concentration in high index material, that there will be a sort of like a gap opening up, because the resonance frequencies of these two modes will be different simply because of their spatial distribution. So this is a rather convoluted way of explaining why this gap will actually open up, starting from a limiting case with infinitesimal index contrasts between the two different layers. So hopefully that gives you some additional insight into stuff that's going on, as well as some opportunity to practice some things we've seen previously with respect to symmetry and resonance frequencies and energy considerations. Okay, to wrap up some terminology here, these two different solutions, the two different bands, they have a certain name, owing to the fact that in one case light is concentrated into the high index region, and here it's concentrated into the low index region. Typically when people study this originally, the low index region is air. So therefore, when light is concentrated into the low index region, they call this the air band over here. And when we're looking at the high index region, then we're talking about the dielectric band. So this is just some piece of terminology. These two bands are called the air band and the dielectric band. Of course, for those of you that remember semiconductor physics, there's of course lots of parallels here, because also in semiconductor physics we have band gaps opening up and periodic structures. There the periodicity comes from like a crystal structure, and we're not talking about air bands and dielectric bands, but rather about conductance bands and valence bands. So there's a clear parallel between these periodic crystals in semiconductor physics and the periodic structures that we've been studying here. And therefore, these periodic structures are sometimes also called photonic crystals in analogy to the electronic crystals that we have in semiconductor physics. Okay. Final remark, perhaps. So what we've been studying here is perpendicular incidence, and we've seen that regardless of the index contrast, even if it's infinitesimally small, this argument shows us that there will be a band gap opening up for normal incidence. Of course, this will no longer be true if we go off axis, right? Because then the effective index contrast decreases. A simple way to understand this, if you have a periodic structure like this, and you're looking not at normal incidence, but at off-axis incidence, in the extreme limiting case of grazing incidence like this, you even no longer have a periodic structure because you're propagating along this direction over here. So that's important to realize. If we are moving off-axis, then slowly the band gap will close. And of course, the higher index contrast you start from, the larger of an off-index angle you can tolerate, but eventually, if you're not careful, this band gap will close again.